Hello and welcome to CS Ninja. This new video series is on data structures and algorithms, and today's topic is binary search trees. But before, we shall establish the concept of general trees, binary trees, and learn a bit about complete binary trees. General trees are simply trees which do not follow any rule. Each node in a general tree can have as many children as needed. A node may have 2 children, maybe 3, maybe 6, and as many children as needed. As I said earlier, it doesn't follow any rule. But binary trees, on the other hand, can only have maximum of 2 children, and that is why they are known as binary trees. Now, what is a complete binary tree? A complete binary tree is a type of binary tree in which every level is complete except the last one, and all nodes are as far left as possible. So, this is a type of complete binary tree, and here is another example of complete binary tree. Now, if I add the leftover nodes to these trees, they become full trees. So a full tree is a tree which has every level complete. So now that we are clear with our basics, it's time to study binary search trees. Binary search trees are further extension of binary trees. Just like any other form of trees, this tree also follows some set of properties. First, all the nodes in left subtree have lesser values, and all the nodes in right have greater values. Here is an example of binary search tree. As we can see, all the elements of left subtree are smaller than 55, and all the elements of right subtree are greater than 55. This should be true recursively for all the nodes too. So 20 is less than 30 and 45 is greater than 30. Similarly, 60 is less than 70 and 85 is greater than 70. Here is another example of binary search tree. Again, left subtree has smaller values and right subtree has greater values respectively. So that is all we need to know about binary search tree in theory, but we are not good programmers if we don't know how to use them. Any type of tree is incomplete without learning searching, insertion, deletion, and transversal. So let's start by searching in binary search tree. Here is an example of BST, and we have to search an element in this tree. Say we have to search for 80 in this tree. So we start at the root node and we compare the value of root node with 80. Is 80 equal to root node? And the answer is no, root node isn't equal to 80. Then we check whether 80 is less than root node. No, the root node isn't less than 80. Then we check whether 80 is greater than root node, and here the answer is yes. That means the element we are searching for lies in the right subtree of root node. And we perform the same action here on 90. Again we ask these 3 questions, and in this case 80 is less than 90. So the element we are searching for must lie in the left subtree. Again we check with 70, 80 is greater, we go right. Now at 80, 80 equals 80. So we have found our element we are searching for. So that's really how you search an element in a tree. Now let us see the time complexity of searching in binary search tree. Consider the same element 80 we have to search in this tree, and we have in total n nodes to search in. As 80 is greater than 50, it must lie in the right subtree of the root node. So just by comparing it with the root node, we are neglecting the whole left subtree. Hence, we have reduced our n nodes to n by 2 nodes with only one comparison with the root node. Now as 80 is less than 90, we have to go to the left and again ignore the whole right subtree. Now as 80 is greater than 70, we go to the right and again ignore the whole left subtree in this process. And finally we have found our node. This process of elimination makes the process really fast. And we calculate this series will account to log n. Hence, time complexity of searching in binary search tree is big O of log n. Now suppose we have a tree like this. In this case, we don't have any right subtree to eliminate. Hence, we are forced to search in the left direction. Hence, in worst case, BST will have a time complexity of big O of n. And same with this case, we don't have a left subtree to eliminate. Now, it's time to learn insertion in BST. It's an important aspect of any data structure, and let's try to add 27 in this tree. Here's a quick note from my side. Insertion is nothing but searching the right place to insert. So we have to perform the searching first and then do the insertion. So let's start at the root node. 27 is less than 50, we go left. 27 is greater than 20, we go right. 27 is less than 30, we go left. And finally 27 is greater than 25, we go right. So this is the right position for 27 to be. We go ahead and write 27 at its correct position, and that's how you can insert any number. Now your homework will be to insert element 11 in this tree and comment down below what your transversed nodes were. Now it's time to learn deletion in BST, but deletion is a bit trickier than insertion. In fact, it has two cases which we have to learn separately, and those are deleting a node with no children and deleting a node with one or more children. Consider this binary search tree. Observe the leaf nodes in this tree. All the leaf nodes are without any children, hence they belong to the first case with no children. And the rest of the nodes belong to the second case. They have one or more children with them. So let's learn these two cases one by one. In the first case, where you have no children, you can simply delete them out of the tree and this won't affect the tree at all. Suppose we have to delete 45 in this tree. We can simply go ahead and delete it. It's really that easy. But in case of one or more children, we have to take a few more things in consideration. We have to learn about two new terms, and those are successor and predecessor. Predecessor is nothing but the greatest element of the left subtree, and successor is the smallest element of the right subtree. Now suppose we have to find the predecessor and successor of the root node 40. So the greatest element of the left subtree comes out to be 35. So predecessor of 40 is 35. In the same fashion, smallest element of the right subtree is 45. Hence the successor of 40 is 45. Similarly, 75 has 65 as predecessor and 80 as successor. Now the concept of predecessor and successor are clear. We can go back to our second case of deletion, that is deletion of element with one or more children. Now what we really have to do in this case of one or more children is to replace the node to be deleted with its successor or predecessor and further delete recursively. Suppose we have to delete 40 from this tree, we will replace the element 40 with either its predecessor or its successor. Let us replace it with its successor, that is 45. After replacing 40 with 45, we have deleted 40, but now 45 appears at two places. So we again have to delete 45 recursively. And as we know, 45 in this case is with no children, so we can simply delete it. So in the second case, we might use the first case too. Keep that in mind. Now we have to delete 75 from this tree. Again we replace it with its successor, that is 80. But 80 appears at two places now. So we recursively delete 82. And 80 has no children, so we can simply delete it from the tree. So that was deletion in BST. In next video we will talk about transversal techniques in BST. If you liked this video on binary search tree and still have any doubts, you can come to my Patreon page and directly ask me as many coding related problems. Thanks for watching. This is CS Ninja.